Hello everyone! This video will be on the 2.6 section of the IBAA curriculum. Please pause the video for a second to look at the concepts, content, and formulae for this section. One sentence that summarizes this section is that a parabola can be represented as a quadratic function which has multiple forms of representation. Until this point in your life, you have probably only encountered straight lines on a graph, or aka linear functions. Linear functions have one crucial meaning, that their gradient is consistent. If you call gradient as a rate of change and consistent as no change, linear functions could be described as no change in rate of change. It all changes as of now. When you look at a parabolic motion, like an example on the screen, the rate of change is not consistent. At first, the gradient is positive, where the graph is going upwards. Then later, the gradient becomes negative and the graph is going down. Not consistent, so there is a change. Thus, you could call that there's a change in rate of change. Change in change, or a meta change. Of many functions that have change in change, the parabolic behavior has an additional feature that there is one and only one vertex or an extrema. Remember from the 2.4 video, a vertex is referred to as the maximum point or the minimum point. The graph on the screen has a vertex at the point 2, 2. Also, the parabola is symmetric. It is symmetric over a vertical line, and the line goes through the vertex point. Thus, the line of symmetry for this function would be x equals 2. Another important feature is that there may be one root, two roots, or no roots. Remember, roots are zeros and also x-intercepts. You can see that there are two intercepts here, thus two roots. Let's look at a similar function just a bit lower. Now, how many roots are there? There's only one. What about now? Now there is no x-intercept. Notice how the functions have not changed much, only the last value changed a bit. Now, let's look at a general form of the quadratic function f of x equals ax squared plus bx plus c. Our functions were all in the general form, and it's nice because it neatly follows a pattern from the gradient intercept form of the linear functions. The general form is especially good at finding the y-intercept, because if x values at 0, it's c. C is the y-intercept. Thus, we know that the y-intercept of the function we see on the screen is 0, negative 6. You see that? Negative 6. It also tells us the axis of symmetry, which can be found on the formula booklet. X equals negative b over 2a. Lastly, this is common to all forms. The a value, or the coefficient of x squared, tells us the direction of the function and how wide or how narrow a function is. If the value is positive, then the function is facing upwards with a smile, or if the value is negative, the function is facing downwards with a sad face. As you can see, it's a sad face because it has a negative coefficient. If the value is between 0 and 1, the function is wider. For example, I could have a function that looks like this, a wider. If the value is greater than 1, the function is narrower. Like that. It works similarly to how the gradient of a linear function determines the steepness of the function. Let's move on to the next form, the factored form. x minus p, x minus q. Do you remember how to factor a polynomial? Well, here comes why we factored all those polynomials, is to put them into the factored form. The factored form is exceptional at finding the x-intercepts. Simple. They're just p0 and q0. However, it is important to note that the factored form is not always accessible. First, there have to be real roots of the function, and second, they have to be simple numbers or rational numbers. Otherwise, things get complicated. Remember one thing, that the coefficient of individual x should be 1. The last form we should know is the vertex form. A x minus h squared plus k. The vertex form, as the name implies, is specialized on noting the vertex of the function, which is h and k. Straightforward, right? Perhaps you might be drowning in despair of having too many forms. Here's how to approach them. Sometimes the question will give you the points to start with, such as intercepts, a vertex, or a random point. When you're given a y-intercept, probably go with the general form. When you're given the x-intercept, go with the factored form. When you're given a vertex, obviously, go with the vertex form. If you're given a random point, well, remember that the points on the function mean that y equals f of x, or in English, if x value of the point is plugged into the function, the result will be the y value of the point. At this moment, you may use any forms, but going with the general form may be a good idea. Then, you might be asked to change to another form. I'll tell you how to do that. Remember that the general form is used for any transitions. Think of it as an interchange station. When you want to go to the general form, simply expand. Expand the factor form, expand the vertex form, and collect like terms, and you will get the general form. I'll show you the abstract version of it. Let's take this one. Let's expand it. Well, first, I would like to expand x minus p and x minus q. X squared minus px minus qx plus pq. And then, let's plug in all the values. Ax squared minus apx minus aqx plus apq. Then, because there's x in the as common terms for the middle two terms, let's put them together. Minus ap plus aq x plus apq. There you go. We see the general form. And also, let's try the vertex form. F of x equals a x minus h plus k. Let's expand it. X squared minus 2hx plus h squared plus k. Plug in the values. Ax squared minus 2ahx plus ah squared plus k. So now we can put the latter two together. So now we're in the general form. If you want to go to the factored form, well, obviously, factor the function. Remember that this is not always possible depending on how many roots are there. Okay, the fun part of this video is going from the general form to the vertex form. This process requires a technique called completing a square. For this one, I'll show you some examples on the sides. first, let's try an example such as f of x equals 2x squared minus 5x plus 1. Okay, first thing I want to do is I want to put brackets around the 2x squared minus 5x. I'm going to exclude plus 1 for now. Then I want to leave x squared without a coefficient, so I'm going to factor out 2. Notice how negative 5 is not divisible by 2. That's okay. Let's just leave them as fractions. 2x squared divided by 2 is x squared minus 5x divided by 2, 5 over 2x. See where this is going? Now, to make this inside the bracket as a square, which we want, we need to think of it. What we want to do, we want to come up with a constant term that completes the square. Okay? To do that, we want to recall that, remember a minus b squared? This is equal to a squared minus 2ab plus b squared. Okay, we have this part so far, and then we want to create this so we can go back to the a minus b squared form. Okay, so what value should that be? We might want to divide this number by 2 because there's a 2 here, and then we're going to square it. Okay, does it make sense? Let's try. So negative 5 over 2 divided by 2 will be, yes, negative 5 over 4. So we're going to add, and then before we do that, we're going to square it again because it's a b squared. So 5 over 2 squared, 5 over 4 squared is 25 over 16. Okay, but we can't just do that, right? We can't just add the number. So what we're going to do is we're going to have the subtraction as well. By doing this, notice how I'm not changing the function at all. I added 25 over 16, and then I subtracted 25 over 16. There's no problem at all. Okay, next point. Now, I'm going to reduce the size of the bracket. So I'm going to put my limit to this part. That means after that bracket, which is minus 25 over 16, will be kicked out of the bracket. Okay? So let's rewrite x squared minus 5 over 2x plus 25 over 16. And then I want to put minus 25 over 16 outside the bracket. So in the process of that, I kind of see it as like a pane of text here. I want to compensate for the 2 where we have as a coefficient here. So let's multiply 2, then we get minus 25 over 8 plus 1. Alright? Almost done. I know that because I forced my bracket to be a complete or a perfect square, I know that this can be written as x minus 5 over 4, which is half of 5 over 2, and then squared. And then let's do minus 25 over 8 plus 1 plus 8 over 8, so that means that's minus 17 over 8. And voila, we have a vertex form now. Let's try that one more time. I'll go a bit faster this time. G of x equals negative 3x squared plus x minus 1. Let's put the brackets around it, and then let's factor out negative 3 minus 1 over 3x. Let's find the half of it, half of 1/3, which is 1/6, and then let's square it, so it becomes 1 over 36 minus 1 over 36 minus 1. And then let's put a limit to it here. So I'm going to rewrite squared minus 1 over 3x plus 1 over 36. And then, as the 36 is negative 1 over 36 is leaving the bracket, we need to pay the tax. So it becomes plus 1 over 12 minus 1. Therefore, we have negative 3 x minus 1 over 6 squared, and then plus 1 over 12 minus 1, so minus 11 over 12. Going from the general form to vertex form may require some practice. I suggest that you do as much practice as possible to smooth out your mathematical processing skill. I hope you enjoyed this video, and try some questions in this section to really master the skills that we have learned. Anyways, I'll see you in the next video. Best wishes!